You are packing for a vacation, but there's a problem. Your suitcase can hold up to 5 kilos of items, but you have over 10 kilos of stuff. Some of your things simply can't come with you. Heartbreaking. To help you with the tough decision of which items to leave behind, you assign each of your things a value representing how much you want to bring it with you. For example, your expensive, stylish sneakers, value 40. That random pen you found at the airport, value 10. Now, here's the problem for you. Which items should you pack so that the final suitcase contains the maximum value possible without exceeding the weight limit of 5? Let's list out the items in their weights and values. And remember, the capacity of our suitcase is 5 kilos. We want to find the maximum value of any combination of these items which doesn't exceed that weight limit. Let's start by considering the brute force approach, where we sift through every combination of items. We would consider each item one by one, and for each item, we can either take this item or leave this item. Keep track of the total weight and value of each combination, and also track the maximum value seen for any valid combination. Then consider the next item. For each combination, you can either add this next item or leave it too. And the same for the next item. If any combination of items exceeds the weight limit, such as this one here, discard it. It's not a potential solution. And keep going until you've built every possible combination of items. The solution is the maximum value seen in any combo which doesn't exceed the weight limit. But the problem is, this approach has exponential time complexity. We're talking 2 to the power of n. It's way too slow. It's so slow I can't even fit all the combinations on the screen, and this is only 5 items. We need a faster way. Take some time to think about the problem. A common first idea people have is let's sort the items by value and pick the most valuable items first, a greedy solution. However, this is not always guaranteed to work. Take the case where you have a suitcase with capacity 10 kilos and you have the following items: one 10 kilo item valued at 100 points, one 5 kilo item valued at 80 points, another 5 kilo item valued at 70 points. If you simply take the highest valued items first, you'd grab that 10 kilo item. But now your suitcase is full, leaving a final value of 100 points. But this is not the optimal solution. If you instead pick the two 5 kilo items, this would give you a total value of 150 points. Way better. This greedy solution fails because it prioritizes value only, but misses the bigger picture. Sometimes it's actually better overall to pack lower valued but lighter items because you can fit more of them in your bag. So you might come up with a second idea. What if we instead order the items by their value to weight ratio? Then the previous example passes. The 10 kilo item has a value to weight ratio of 100 over 10, which is 10. The first 5 kilo item has a value to weight ratio of 80 over 5, which is 16. And that's better than the first item. The second 5 kilo item has a value to weight ratio of 70 over 5, which is 14. And that's also better. So this suggests that the two 5 kilo items have a higher value per kilogram. So picking those first would make sense, right? You end up with the best bag, right? Well, in this scenario, but it still falls apart in some cases. Take a simple counterexample. Having the highest value to weight ratio, you pick the 7 kilo item. But now you can't fit any more of the items in the suitcase. So you stop there, leaving a total value of 70. But this is not the best solution. Again, picking those two 5 kilo items leads to the higher total value of 80. So once again, this strategy fails because it's not really seeing the forest for the trees. It's looking at the items one by one rather than considering the best combination overall. So we need something a bit smarter here. Enter dynamic programming. This is known as the 0-1 knapsack problem and is seen as a bit of a dynamic programming classic. In this problem, you are given a list of items. Each item has a weight W and value V. You are also given a maximum capacity of your knapsack or bag, W. This is 5 kilos in our example. Now the goal is to select the subset of items such that the total weight doesn't go over the limit and the total value is as high as possible. But how do we actually do that? And what even is dynamic programming? Dynamic programming is an algorithmic technique often used for optimization problems. The core idea is to break a larger problem into smaller, overlapping subproblems. Then you typically solve each subproblem only once and store the results. By combining the solutions of these smaller subproblems in a clever way, you can build towards the solution for the overall problem. And this is exactly the kind of strategy we need to pack the perfect suitcase. Let's build up the solution to the knapsack problem together. We're trying to pack a suitcase with a maximum capacity of 5 kilos. To be honest, it's a lot to think about. So suppose instead of 5 kilos, our suitcase has a capacity of just 1 kilo. What's the maximum value we can pack then? To solve this, we will create a table to track the best value we can get at each step. So each row of this table, I, represents how many items we are allowed to use, and each column, J, represents the current capacity of the suitcase, 0 through to 5. In other words, cell IJ stores the best value we can pack into a bag of capacity J using only the first I items. And the idea is we build up to our total capacity of 5 kilos by considering smaller capacities first. So for example, the cell in row 3, column 1, will store the maximum value we can pack into a 1 kilo bag using the first 3 items. Row 4, column 3, would store the maximum value we can pack into a 3 kilo bag using the first 4 items, and so on. So before we begin, we need to set up some simple base cases. Firstly, row 0. Remember, rows represent the number of items we are allowed to use. So row 0 represents using the first, 0 items. Of course, the maximum value we can get if we don't pack anything is 0. So this entire row is just 0. And we include column 0. The columns represent the capacity of the suitcase. So column 0 represents a suitcase with 0 capacity. Of course, a 0 capacity bag cannot fit any items in it, so its maximum value is also always 0. Base cases, base cases. Now we are ready to begin. So starting in cell 11, this represents the best value we can pack into the 1 kilo capacity bag using only the first item. The first item weighs 1 kilo with a value of 10. In each step, we have a decision to make. We can either skip this item and instead keep the best solution found so far for the current capacity. That is, we just keep the solution we got using the previous items stored in the cell directly above this one. Or we can take the current item and combine it with the optimal way to pack the remaining capacity to reach the current capacity. This will become clearer later, but you can think of it as combining the 1 kilo pen with the best way to pack the remaining 0 kilos to reach the 1 kilo capacity we're currently considering. Skipping the pen gives us a value of 0, the pink square, and taking it gives a value of 10, the 2 yellow squares. So we take it. I like to call these two options skip it and keep or take it and combine. Moving on, item number 2 has a weight of 2 kilos, which is too heavy for the little 1 kilo bag. It simply doesn't fit. When an item is too heavy for the current capacity bag, we can only do option number 1, which was to skip it and keep the previous best solution. So in this case, the best value we can get out of the first 2 items is still 10. Item number 3, the sneakers have a weight of 3 kilos, so they are also too heavy for our 1 kilo bag. We skip it and keep the previous best solution of 10. What about the 4th item, the toothbrush? It has a weight of 1 kilo, so it can fit. This means we consider both choices. We can either skip this item and instead keep the best value we found so far, 10, or take this item and combine it with the best way to pack the remaining 0 kilos using the previous items to reach 1 kilo. Well, the toothbrush has a value of 20, which is better than the maximum value found so far of 10, so we take it instead. The optimal value we can get by considering the first 4 items is now 20. The next item, the headphones, is 4 kilos. It is too heavy for our 1 kilo bag, so we skip it and keep the previous best solution of 20. 20 is the overall best possible solution for a 1 kilo capacity bag, achieved by packing the toothbrush. Suppose our bag can now carry 2 kilos worth of stuff. Can we repeat the process to find the best value we can pack into a 2 kilo bag? Yes, and we can use the solutions we found to pack the 1 kilo bags to help us. Here's how. So start with the first item. It's only 1 kilo, so it can fit in the 2 kilo bag. We can either skip it and keep the best value found so far for this bag size, which is 0 because we just started, or take it and combine this 1 kilo item with the best way to pack the remaining 1 kilo now to get to the total weight of 2 that we're considering. This gives a total value of 10. So the best value we can get from the first item is 10 again. The second item has a weight of 2 kilos, which now can also fit in the 2 kilo bag. Remember, we increased the capacity of the bag to 2 now. Again, two choices. Do we skip it and keep the best bag made out of the previous items, 10? Or do we take it and combine this 2 kilo item with the best way to pack the remaining 0 kilos found so far? Taking item number 2 gives the higher value, so we take that instead. Best value we can get out of the first 2 items is 25. The third item is too heavy for our 2 kilo bag, so we can only skip it and keep the previous best solution. The best value from the first 3 items is still 25. The fourth item, weighing 1 kilo, is where it gets interesting, and hopefully with this example it will click for you. Remember our 2 options. We can either skip this fourth item and keep the best value we got from the first 3 items, 25, or take this fourth item and combine it with the best way to pack the remaining 1 kilo using the previous items. Why? Because this 1 kilo fourth item, the toothbrush, plus the best way to pack 1 kilo using the first 3 items, adds to a weight of 2 kilos, i.e., the capacity of our current bag. This is a better solution than the previous one, worth only 25 points. So the optimal 2 kilo bag using the first 4 items is 30. Finally, the fifth item is 4 kilos, which is too heavy for the 2 kilo bag, so 30 is the best value overall for a 2 kilo bag. To drive the idea home, let's move up to the 3 kilo bag. Item 1, nothing is packed so far, so of course we take it. The best value so far is 10. Item number 2 is 2 kilos. Remember those options I told you about. Skip it and keep the best solution found so far, a value of 10, or take it and combine the 2 kilo camera with the best way to pack the remaining 1 kilo using the previous items, because that adds to 3 kilos total, our current bag size. That leaves a value of 25 plus 10, which is 35. It's better, so we do it. Item 3 is 3 kilos. We can either skip it and keep the previous best solution of 35, or take it and combine this 3 kilo item with the best 0 kilo packed using the previous items. This is the better choice as it has value of 40. Item number 4 is 1 kilo. We can either skip it and keep the previous best solution of 40, or we can take it and combine this 1 kilo fourth item to the best 2 kilos made from the first 3 items to give a total value of 45. This is better, so we update again. Finally, item number 5 is still too heavy for the 3 kilo bag, so we are forced to skip it and keep the previous best solution of 45. 45 is then the overall optimal solution for a 3 kilo bag. I will keep going through the table until we find the final answer, but at this point in the video, I strongly encourage you to try and fill out the rest of the table yourself first and then compare answers. So then the overall optimal solution is 70. 70 is the best value we can pack into our 5 kilo suitcase after considering all the items. And these are the items we packed: the pen, sneakers, and toothbrush. Let's go through the algorithm to solidify what we really did here with another example too. Knapsack Solver is going to return an int, which is the optimal value we can pack. For the inputs, we are given a list of weights where weights I stores the weight of item I, and a list of values where values I stores the value of item I. Here are the weights and values of the items in this new example. Then we are given the capacity of our suitcase, big W. In this example, let's make it 10 kilos. The first step is to make that table. DP is an n plus 1 by w plus 1 table where each cell, ij, stores the best value we can get for a capacity j bag using the first I items. Why n plus 1 and w plus 1? Because remember, we have the base cases of packing a zero capacity bag and including the first 0 items. We can insert a dummy item of weight 0 and value 0 in our weights and values list to represent this base case. These base case cells all have a value of 0 because remember from earlier, the 0th row represents packing the first 0 items, which always gives a value of 0. In C++, we can do this by simply pre-allocating the table to have all zeros. Now we can loop through each item in the grid from I equals 1 to n. And for each item, consider each capacity from j equals 0 to w. Remember, dpij is going to store the best value we can pack into a capacity j bag using the first I items. So at each cell, dpij, remember our two choices. Option 1, skip the current item and simply keep the best value so far using the previous items. That is stored in the cell directly above this one, the bag with the same capacity but only using the first I-1 items, dp I-1j. Or option 2, take the current item I and combine it with the best way to pack the remaining capacity. That gives a total value of the current item's value plus the best value achievable for the remaining capacity using the previous items. The remaining capacity after taking this item is given by the total current capacity, J, minus the weight of this item to find the remaining weight. For example, if the current bag we are trying to fill has capacity 6 kilos and the current item has a weight of 2 kilos, we can add it to the best way to pack the remaining 4 kilos using the previous items, because 4 kilos plus the current item weight of 2 kilos takes us up to the current bag capacity, 6 kilos. But of course, if the current item is larger than the current bag's capacity, we can't add it at all. So option number 2 is only considered when the weight of the current item is less than or equal to the capacity of the current bag, J. For example, the weight of this item is 7, but we are trying to pack a 5 kilo bag, as we are in column 5. It won't fit, so all we can do is take the previous best solution found for this bag, 25. To solve the subproblem in each cell, ij, we take the maximum of these two options. After all, we want the best value bag. And we loop through and simply fill in each cell. This is a classic dynamic programming problem because at each step we solve a subproblem using the answers to previous subproblems to help, and we build up to the overall answer. So now we've built this table, which cell actually holds the overall answer? It's the bottom right one, dpnw, because this is the cell we built up to. It stores the optimal value for the 10 kilo bag after considering all n items. Isn't that cool? And I wrote a function to output the table to show you. With all this value packed into one suitcase, one question remains: which items actually ended up making the trip? In other words, suppose we actually wanted to return a list of the items packed in our optimal bag rather than just the total value. The way to solve this is to simply backtrack through the table we built up and try and decide, did we take that item or not? So look at the table again. We finished in cell NW. So let's start there and use I and J to keep track of our current position. Now we are going to backtrack until we get to the first item, so while I is greater than 0. Before we begin, let me pose the question to you. Did we need to pack item number 8? If you said no, then that's correct, because look at the cell directly above it. This stores the optimal way to pack the same bag, the 10 kilo final bag, but using only the first 7 items. And the value of this bag, but without item number 8, is the same. So we can actually get this optimal result of 65 without using the 8th item. Item 8 was not included in our bag. So first check, if the current cell is equal to the cell directly above it, we didn't need to take the item in the current row, and we can just move up a row. Now, did we take item number 7? This time the answer is yes. Look at the cell directly above it. The optimal value using the first 6 items is only 60. but the optimal value using the first 7 items is 65. Clearly, we added item number 7 to the bag to achieve a higher value. So if the current cell is not equal to the cell directly above it, we must have taken the item to achieve that higher value. So we can add it to our taken items list. But then which cell do we go to next? To answer that, we need to work out which partially filled bag did we add this item to. This item has a weight of 1 kilo, so we added it to a capacity of weight 1 less than the current bag, using the items before this one. In other words, we added the 1 kilo item to the 9 kilo capacity bag to make the 10 kilo final bag. So let's go to that cell next. We go backwards, subtract the weight of this item from the current column, and move up a row. Now we ask, did we need to take item number 6? Again, look at the cell directly above it, 45. We achieved a better value once this item was included, 55. So item number 6 is packed in our bag. Now, item number 6 has a weight of 5 kilos, so we added it to the optimally packed bag, which is 5 kilos lighter than the current bag, using the items before it. So let's go there. Item number 5 was not taken because the cell directly above it is equal to it. In other words, the value didn't improve by considering this item. We can achieve the optimal value for this bag by not taking this item. So move straight on up. Same with item number 4 and item number 3, not taken. Item number 2 was taken because it increased the value compared to the previous items. It has a weight of 4, so it was added to the optimal bag 4 kilos lighter than the current bag, using the items before it. So we move to that cell. Finally, item number 1 was not taken because the value didn't improve. The cell above it is the same. Now we've processed all of our items, so we can return this list as the list of items which gives the optimal value. Items 2, 6, and 7. We claim this is way faster than brute force, but just how fast is it? Well, look at the size of our grid. There are n plus 1 rows for the items and w plus 1 columns for the capacities, so that's roughly the size of n times w. Now for each cell, we decide whether to keep the previous solution or add the current item's value to a smaller bag. Since we stored the solutions to both of these choices, these are constant time O1 lookups. No recomputing or recursion needed, just a simple decision. And this constant time lookup is performed for each cell, so the total time complexity is the number of cells, O(n) times W. Now, what about the space complexity? Again, this is just the size of our grid used to store the subproblem results. Big O of n times W again. But I'm going to give you a challenge to try and solve on your own. This space complexity can actually be improved to just big O of W. In other words, can you adjust the algorithm to find the optimal value using only OW extra space, i.e. using only one row or a constant number of rows of size W? If you are brave, there's actually a way to do it even in just one row. So leave your answer in the comments. Anyway, thanks to dynamic programming, you were very happy with the suitcase you packed for your vacation and you had a great time. See you next time.